The defined targets for the development of the future European civil aviation require more environmentally friendly and fuel-efficient aircraft. In this context, laminar flow technology is becoming more and more important as the laminar flow around the surface is characterized by lower friction than for turbulent flow, which leads to a reduction of aerodynamic drag and fuel consumption. By generating enhanced laminarity based on shape optimization of components exposed to the flow, which is called natural laminar flow, NLF, there is a reduction on the complete aircraft drag of around 10%. While the major contribution is provided by innovative wing profiles, further potential is available on the nacelles and the horizontal tailplane, HTP, where additional savings of 1% and 2% respectively are envisaged. Compared to a laminar boundary layer, the turbulent one exhibits an intermittent momentum exchange perpendicular to the main flow direction. The resulting increased surface friction is linked to higher wall shear stress and an increased heat transfer. The key feature for the aerodynamic quality assessment of laminar wings is the localization of laminar and turbulent boundary layer flow regions by using the capability of temperature-sensitive paint, TSP. In order to make use of the different heat transfer across laminar and turbulent boundary layers, for a visualization of the transition line, the natural small temperature difference between the surface and the outer flow has to be amplified. In a cryogenic wind tunnel such as ETW, this temperature difference may be generated by a small step of the incoming gas flow temperature induced by either increasing nitrogen injection or stopping any injection. This method is well established at ETW and is known as the temperature step. However, this approach reveals a deficit. Changing the temperature also changes the Reynolds number, which may influence the results. Furthermore, performing transition assessment during a continuous pitch polar, therefore varying the angle of attack of the model, is not feasible. To overcome this drawback, two new alternative heating approaches will be validated within the scope of BinCola. This totally new approach within the BinCola project involves heating the surface by means of an infrared laser beam. A new generation of diode lasers in the multi-kilowatt class are able to heat a cold surface of -160 degrees Celsius by several degrees to enable permanent visualization of the laminar and turbulent flow regions. The laser radiation itself is within the infrared spectrum and is not visible to the human eye or to standard observation cameras. The active TSP molecules on the surface are excited by a blue LED light and in return emit a red light. The major advantage of the laser-based concept is that the high-energy infrared laser light is transferred via a glass fiber into the cold and pressurized wind tunnel. In parallel to heating with a laser beam from outside the tunnel, another heating concept was investigated: the heating of the surface layer by means of CNT, carbon nanotubes. Underneath the active temperature-sensitive paint coating, an electroconductive layer is powered to generate the required temperature difference. The effort required to produce several coats of paint is certainly higher than for the laser heating method previously outlined, but offers the advantage of operating in the shadow of radiated light. This feature is an advantage in terms of investigations made on highly curved surfaces, for example, nacelles. Before entering the ETW tunnel, the most suitable measurement technique has to be proven within the pilot facility of ETW. A generic nacelle based on a two-dimensional profile with NLF technology was designed and manufactured. The different coatings as described above were applied, and the final polishing achieved a mirror-like surface with a surface roughness less than 0.02 microns. In order to generate the exact geometry and surface quality, the coating has to be applied very carefully. Within the BinCola project, the initial profiling of the surface has been achieved by a new machining process, since the surface accuracy could not previously be achieved by hand. The model was fixed in the test section of the pilot tunnel and was observed from glass windows in the top and sidewall by 2 cameras. Infrared laser heating, blue LED excitation, and CNT heating were installed. The entire equipment was located within the insulation of the wind tunnel walls. The flow conditions in the wind tunnel can be changed by altering the speed of the compressor and the rate of nitrogen injection. The adjustment of the flow parameters is precisely controlled, so that the Mach number can be controlled with an accuracy better than 1 millimach. Changing flow parameters will have an influence on the boundary layer transition, which can now be visualized. Accordingly, parametric studies with continuously changing angle of attack are now feasible, which is significantly more efficient than the temperature step method. The continuous TSP method is a very powerful tool for test engineers and researchers in order to optimize the wing shape and aircraft geometry. Physical flow phenomena can be studied experimentally to enhance understanding and to enable validation of numerical simulations. Another new approach within the BinCola project is the application of the different layers of the active paint layer, especially on the highly curved surfaces of the nacelle. The coating is applied in a small pocket of about 1/10 of a millimeter, comprising primer, insulation, carbon nanotubes for heating, a second insulation layer, and finally, the active temperature-sensitive paint on top. The BinCola project is an important step towards further improvements of laminar flow aircraft by providing high data quality with increased efficiency. The benefit of innovative concepts of a laminar nacelle and HTP installed on the business jet configuration could be shown. By using ETW, this insight is already available during the design phase of an aircraft, resulting in risk mitigation and cost savings associated with avoiding later expensive modifications.